Today's lecture is about fastener and member stiffness in bolted joint connections. So specifically learning how to calculate these things. And we're going to do it through an example. This is a water pipe at the WRF on campus, and it's got 16 3/4 10 UNC bolts. We've got narrow washers on both sides and regular nuts on the sides with the threads. Now, in reality, it's actually threaded rod throughout, and there's nuts on both sides, but I'm going to pretend for the sake of the analysis that it's a regular old bolt. The analysis with a threaded rod is actually easier. It's just that the whole length inside the grip is going to be threaded, as opposed to a bolt. If it were a bolt, then we're going to learn how to figure out what the unthreaded length was going to be and treat that separately from the threaded portion of the length, because they're going to have different areas over which different stiffnesses as a result. So it's going to make the stiffness calculations a little bit more complex, and that's why we're going to try it that way. The total thickness of the plates, so we've got like a flange on the end of the pipe, and we've got water pressure that's being held on by this cap here. The total thickness of the flange plus the cap is 2 inches. Let's say that the pressure of the water, actually I was told by a student last year that they've seen it go up to 100 psi, and they told me that the inside diameter of these pipes was 18 inches. So this pressure is acting over that whole 18-inch circle. So we've given that steel pipe, it's got the operating pressure of 100 psi, and the gasket has a diameter of 18 inches. The combined thickness of the flange and the cap is 2 inches, and the cap is secured by all those bolts. What is the total tension in each of the bolts, and is it less than the proof strength of the bolt? Is the bolt going to fail? So our strategy here is going to be, well, we need to determine the tension in the bolt and see whether it's less than the proof strength, right? So our equation here is the tension in the bolt, less than or equal to the proof strength, P for proof, B for bolt. So how do you calculate both of these? Well, we've talked about in previous lectures that the proof strength is the product of the proof load is the product of the proof strength, which is a stress, load being a force, is the product of the proof strength and the tensile stress area of the bolt. And the proof strength of the bolt, you just look up in a table. You can actually also look up for your bolts what AT is. So we're going to go through that process. But on the left-hand side of this equation, we've got the tension of the bolt. That's the sum of Fi, the initial force in the bolt, the preload of the bolt, plus P sub B. Let's change that to a lowercase b, which is the load in the bolt, the tension in the bolt that is caused by P, the externally applied load, I guess is the way to say it. It's tension in the bolt that's caused by the externally applied load. So we've got some preload that's due to the fact that you torqued the bolt, and then PB, the externally applied additional tension in the bolt. What is the preload in the bolt? Well, that depends on whether you have a permanent or non-permanent connection, or really how much you torque the bolt. But the recommendation is that you should set a preload for non-permanent connections to 75% of the proof load of the bolt, which we've already calculated. Now, this additional tension in the bolt that's due to the applied load is given by C, the joint stiffness constant or coefficient, times P, which is the externally applied load per bolt. C we can calculate if we knew the stiffness of the bolt and the stiffness of the member, which is the material in between the bolt in that sandwich there. It's this ratio here. And then P, the externally applied load per bolt, is the total applied load in this case, the pressure times the area in this case, divided by n, the number of bolts. We're going to assume that it's equally divided among all of them, which is a reasonable assumption because of the symmetry in the problem. Now remember here, the additional tension in the bolt that is due to the applied load is some fraction, C, that's less than 1. You can tell that this is less than 1 if these are positive numbers. The denominator is the sum of these two, which is greater than the numerator, so this is less than 1. It is a fraction, less than 1, of the applied load per bolt. And what we're after here is how to figure out for a given bolted joint that you might be designing, what is C here? And how do we figure out what the KB and KM are in order to calculate what C is? So that's what this module is really about, is calculating those stiffnesses. So to get started, we really have to look at, well, in my book, this is version 9, page 426, table 8-7, but there's a similar table in the 10th and 11th editions, and so you can find something that looks like that. It is the suggested procedure for finding the fastener stiffness. So I'll zoom in a little bit here. Let's talk about the different, these two different diagrams here. We've got an A and a B. And we've got a little bit different instructions depending on whether we're looking at something that looks more like figure A or something that looks more like figure B. Let's talk about these different dimensions. D, the major diameter of the bolt, right? The total length of the bolt, capital L, is from the bottom of the head, the base of the head, to the very tip. That's not a super important parameter of the problem, or it's just kind of an intermediate thing. What we're really going to be after is what is lowercase l sub d, which is the distance between the head of the bolt to the beginning of the threads. The run out is what it's called, where the threads begin. And that, look, this is a cylinder of a constant radius that's the major diameter of the bolt times 2, or divided by 2, I guess. And so it's going to have, this is just a cylinder of steel. It's going to have a stiffness associated with it. And then also we're going to have this threaded portion here, which is going to have a length L sub t, lowercase lt, which is the part of the grip. I guess lowercase l is the grip, the part that's in between the base of the head and the nut. That's lowercase l. It's the part of the grip that's threaded. And this has a different area, effectively. It's a bit like a cylinder of a different area because it's got the threads on there. It's going to have, you're going to use the tensile stress area for calculating its stiffness instead. Notice something between the lowercase and the uppercase. Lowercase is related to the grip length. It's the part of the fastener that is sandwiching material between it. The uppercase L is the whole length, is what it's referring to. So uppercase, you can think of whole length, the entire length, and lowercase l is grip length. And it's consistent when we're talking about L subscript t. If it's a capital L, we're talking about the whole threaded length. Whereas a lowercase l subscript t, we're talking about the portion of the threaded length that's within the grip. And similarly here, lowercase l sub d is the portion of the unthreaded length that's within the grip. But the unthreaded length is the same, the part of it that's in the grip and the whole of it. It's always, all of it is always in the grip. So we could give this a symbol capital L subscript d as well. We've got a situation like this. We've got a bolt, and we've got a washer, and we've got a nut in the end. Actually, we've got a washer on this side as well. In our case, we said there's washers on both sides. We've got a bolt situation as opposed to a screw situation. We call the same fastener a screw when it threads into a part and doesn't have a nut on the other end. So A and B, different procedures. We've got procedure A that's relevant to us here. So the first thing, we're just going to follow this to the letter. If we've got a fastener diameter D, yep, we've got it. It's 3/4 of an inch. A pitch P. What's the pitch in this case? Well, we've got 10 threads per inch, so let's find out what the pitch P is going to be. P, the pitch, is 10 threads per inch. So it's actually just 1 over the number of threads per inch is equal to 0.1 inches. What's the washer thickness? Well, we get it for a fastener with this diameter from table A32 or A33. Well, in my book, I'm jumping over to page 1056 for this, and it just says what the dimensions of standards are. And we've got the fastener size. Well, we've got a 3/4 inch fastener. Now, I said it was a narrow washer instead of a wide washer. N for narrow, W for wide. So if it was a narrow washer from the problem description, then the thickness here, this column here, for a 3/4 inch, and when we're talking about narrow washer, is 0.134 inches. So T, the washer thickness, is 0.134 inches. What's the next step in the procedure? It says find the nut thickness, H, from table A31. Okay, so we go to table A31, And we find for the nominal size of the nut, which is 3/4 inches, we are interested in the height, h, of the nut we have. We've got a regular nut, it said so in the problem statement, and the regular nut has a height, h, of 41/64. Okay, so that's the first few parts of our procedure here. I just wanted to show you that these are reasonable things and what it looks like when you're actually choosing or doing some design work. So McMasterCar.com, we've talked about using that before. It's a good source of parts. And let's take a look at what the height of nuts are that work for 3/4 inch bolts. So let's say we've got hex nut, medium strength, just whatever the first thing it gives us is. And we're talking about for a thread size, 3/4 10. And look, the height of all these nuts is 41/64. So the table in Shigley is giving us reasonable information. Now there might be nuts that are a little bit longer than that, etc. But what Shigley is giving us for kind of common ones is pretty reasonable. Same sort of thing for washers. Okay, I'm just going to pick a washer, general purpose, nothing too special. For a screw size, 3/4. And we see that there's actually a wide variety of thicknesses of washers and inner and outer diameters, and it's all over the place, right? But what was our thickness? We said 0.134, and that's in the range that we've got here. Some of these are a little bit thinner. This one is within this thickness range. It's within this thickness range, so it's a reasonable number. I would, if you're doing this carefully and you're doing it for a real design, well, pick out your washers and then, know what the thickness of those are. The recommendations in Shigley, these suggested numbers are for doing back of the envelope calculations when you haven't actually chosen your parts, just getting kind of approximations. Okay, so the next step is to find what the grip length L is, and we're talking about a situation like in figure A, and it says the grip length is the thickness of all material squeezed between the face of the bolt and the face of the nut. Now we've got a washer on this end that's squeezed between the face of the bolt and the face of the nut. We've got another washer on this end, and then we've got the sandwich of material in between. So from our original figure, I said that there was a washer here, there was a washer on the other side, and there's a 2-inch sandwich in between. So it's the 2 inches plus 2 times the thickness of the washers is our grip length. And the grip length was 2 inches plus twice the washer thickness. This was 0.134 inches, and that number is 2.268 inches. What's the next step? From that, we can find the fastener length. We need a fastener with total length L that's greater than the grip length plus capital H. This is just from geometry. We need a fastener that is at least as long L as the grip length plus the height of the nut. I mean, you can see there needs to be threads sticking out. When we install this, it has to go all the way through the nut. It can be a little longer, that's fine, but we need to choose some sort of fastener that is greater than the sum of those two things. So let's go ahead and calculate what this is, what this L plus H is. We need the total length of the fastener to be greater than L plus capital H, which is equal to 2.268 inches plus 41/64. That means it's equal to 2.91 inches, and L has to be bigger than that. The total fastener length has to be bigger than that. We're going to choose a fastener from that table A17. Table A17 says that the next largest, we've got 2.91. The next largest is 3. And these list preferred sizes. So 3-inch fastener is what we're going to pick. L is equal to 3 inches. And let's also see that on McMaster. So if we go to bolts, hex head screws, we had, let's use grade 5, that's kind of medium strength. 3/4 10. Looks like some are fully threaded. You can get bolts that are fully threaded, and you can get ones that are partially threaded, and Shigley is telling you that is giving you how to estimate what those minimum threaded lengths are going to be, and we're going to see that in a second. But look, we've got kind of preferred sizes here: 2, 2 1/4, 2 1/2, 2 3/4, 3 inches. There's not one that is 2.91 inches long. We have to pick from one of these preferred sizes, and Shigley's fraction of inch table does a pretty good job of telling you what those are without you having to look up a particular part number. Okay, so assuming it's a partially threaded fastener, the size that we're going to need, the length we're going to need is 3 inches. So let's move on. The next step is to figure out what the total threaded length, L subscript T, is. If it's an inch series bolt and its total length is less than 6 inches long, which it is, it's only 3 inches, then the threaded length, LT, is 2 times the diameter plus 1/4 inch. So LT is 2 times the diameter plus 1/4 inch. That would be 1.75 inches. What does McMaster say about that? Well, yep, for a 3/4 inch bolt, the minimum threaded length for any of the partially threaded fasteners is 1 3/4 inches. When we start getting above 6 inches, when it's greater than that, we've got a 2-inch minimum threaded length. Let's see what Shigley has to say about that if Shigley agrees. If it's greater than 6 inches, then we add a 1/4 inch to it. So, yep, exactly what Shigley said. So Shigley, again, just a handy way to give you an estimate of what you're going to find in a catalog of real parts. Okay, what is the length of the unthreaded portion that's in the grip? And this is just geometry. The unthreaded portion, lowercase ld, is equal to the total length of the fastener minus the threaded length of the fastener. You can see here, this part, L sub d, is equal to the total length of the fastener, L, minus capital L sub t, right? This threaded portion. Remembering that, maybe we should write the equation capital L sub d is equal to capital L minus capital LT. Maybe it makes more sense if you think about it like L is equal to LT, the threaded portion, plus LD. That makes it really obvious, right? Well, LD then is equal to L minus LT, and LD is really itself equal to lowercase ld, because the portion of the fastener that is unthreaded is equal to the grip portion, the portion within the grip that's unthreaded. So actually what I'm going to do is I'm just going to replace this symbol with lowercase l sub d, and we're going to calculate this. It is 3 inches minus 1.75 inches is equal to 1.25 inches. What's the next step? Find out the length of the threaded portion that's in the grip. That is the grip length minus L sub d, the portion that is unthreaded within the grip. So lowercase l sub d is equal to L minus L sub t. The total portion that's in the grip is the unthreaded portion plus the threaded portion. We could say the total portion that's in the grip is equal to the threaded part of that plus the unthreaded part of that. And that's going to tell you how to find L sub t. L sub t is equal to L minus LD. Looking at our numbers, 2.268 minus L sub d, which was from above, 1.25, we get 1.018 inches. Then it says, find the area of the unthreaded portion, find the area of the threaded portion. So A sub d, the area of the unthreaded portion, is pi major diameter squared divided by 4. That makes sense. We've got just basically this portion is just a cylinder with radius d or diameter d. So let's go ahead and calculate that. 0.442 inches squared. It says the area of the threaded portion is the tensile stress area from table 8-1 or 8-2. Depends on whether you're using metric series or not. 8-2 looks like it is for UNC threads. So we've got a 3/4. It is the 10 threads per inch. And it has a tensile stress area. Tensile stress area for the coarse version is 0.334 inches squared. We know that the deflection of a cylinder, a cylindrical rod, is equal to the force, like PL over EA, right? We've seen that before. So the stiffness, which is basically the force divided by the deflection, force per inch of deflection, is equal to EA over L. And what we're saying is E, well, it's the elastic modulus of steel, which is 30 times 10 to the 6 psi. And A, well, if we're talking about the unthreaded portion, it's going to be this. If it's the threaded portion, it's A sub T. And then length, well, if we're talking about the unthreaded portion, it's L sub D. If we're talking about the threaded portion, it's L sub T. So we can kind of just apply this in order to find the individual stiffnesses of the two parts. So let's try that. K of the unthreaded portion is equal to E times AD over LD is 30 times 10 to the 6, 0.442, 1.25 inches. We've got 10,602,875 pounds per inch, very stiff. KT, use the threaded area, the tensile stress area, over the threaded portion that's within the grip. So that's 0.334 inches. Threaded portion that's within the grip is 1.018 inches. 9,842,829 pounds per inch. Right, and these are springs that are in series, so we kind of remember that we can add them and find the total stiffness. 1 over the total stiffness is equal to 1 over K, so the stiffness of the bolt, 1 over K of the bolt is equal to 1 over KD plus 1 over KT. You could rearrange this, you could figure out that KB is KD KT over KD plus KT. We're just substituting in these two numbers here. 5,104,362, or I guess this is really a 3 pounds per inch, which is one of the things that we were after, the stiffness of each of the bolts. Now there's a formula in the book that is basically just substituting all this together. You could just use this formula, and all it's done is exactly what we have. You see these same sorts of equations that we've got. They've just substituted in AE the areas and the elastic modulus and all that into our equation from before. So if you prefer, you can, instead of calculating the stiffness of the threaded portion and unthreaded portion separately and then adding them as springs in series, you could just use this equation here. I just wanted to show conceptually where that was all coming from. Okay, the next thing we might want to find is the stiffness of the material that is within the grip, the member stiffness. And there's two ways that we can do that, and they're going to give us approximately the same answer. So I'm going to show you the equations in the book that are relevant here. So all this is derivation, and it boils down to this equation being really useful. If you've just got a consistent material, if it's both sides are the same material of your sandwich, or everything in your sandwich is the same material. Like in this case, both sides are the same sort of steel. If we had one that was aluminum, one that's steel, this equation isn't going to be valid because we're going to have different elastic moduluses. But if all of it's steel, it comes down to you get a stiffness of the member that is given by this. All right, so let's take a look at what these things are here. We've got E, which is 30 times 10 to the 6th. We've got D, which is 3/4. Again, we've got D is 3/4, and same thing here. And these L's are the grip lengths, 2.268 inches. So if we were to plug all that in, we get 20,986,874 pounds per inch. And then that formula is kind of long, so they have an approximate formula that's based on a research paper. stiffness of the member divided by the elastic modulus, the material divided by the diameter, is equal to, some exponential function. And so if we want to find the stiffness of the member, then we are going to just multiply both sides by ED. So this equation is telling us that Km is equal to ED, elastic modulus, major diameter of bolt, of some constant A. This is a constant. We're going to look it up in a table. exp, that's the exponential function, e to the power of b, some other constant, times the major diameter of the bolt divided by the grip length. So if the entire joint is made up of the same material, their constants for steel, A is 0.787 and for B, 0.628. So if you had a joint that was entirely made up of aluminum, then you would use this A and this B instead. One of the main things, though, to keep in mind is A in this case is not the area. It's not any area. It's just a constant. These are two constants that are coming from the table in the book. This A is given by the table, and this B is given by the table. Right? We've got D, which is 3/4. We've got L, 2.268 as before. We've got another example of D, and then we've got elastic modulus, 30 times 10 to the 6. So if you plug all that in, you'd get 21,803,973 pounds force per inch. Look, these are two different methods for calculating the stiffness of the member. We don't have just one formula because there's not one that perfectly describes reality. We're going to have to make approximations in either case. This one was based on some theory that said that the stresses are going to distribute themselves over a cone, and we're going to kind of figure out how squishy is that material it's where the stress is experienced, versus this one, which is kind of FEA driven. They did some curve fits based on FEA experimental data. I mean computer experiments in this case. And look, we get a similar result. So we could pick something in the middle of these two. We could pick one of the two. It's our choice as engineers. We see that they're similar and they're not going to affect the outcome of our problem, probably. They might affect the exact factor of safety, but probably not whether the joint is safe or not. So let's go ahead, and for the rest of this, we're going to use that the stiffness of the member inside the joint is 21 million. So again, looking at our strategy, one thing that we needed these KB and KM for was in order to find capital C, the joint stiffness coefficient. Let's go ahead and write that. Let's actually take a screenshot of this. This will help guide the rest of the analysis. All we've done so far, by the way, is figure out what KB and KM are, but the rest is easy, right? You can see all the equations here. So we're just going to plug and chug really for the rest. It's all stuff that we've done before. Our KB is this number. Our Km, we said we're going to use this number. And so our C, if you plug those things in, we're going to get a C of 0.1897. So in order to find the applied load per bolt, P, we have to find P total, our total applied force. That's equal to the pressure, which was 100 psi on the cap, times the area of the gasket. So that's 100 psi times, well, it's pi times some diameter, the diameter of the gasket, that was 18 squared, divided by 4. So the total force acting on that cap is, trying to pull it off, is 25,447 pounds. And the total number of bolts is 16. And so our applied load per bolt that's trying to pull each bolt away is that 25,000 divided by 16 is 1,590.43 pounds. Okay, so let's fill in from these numbers here. 0.1897 is our C, 1590.43. Well, C times P, that's 301.7 pounds force in each bolt is the additional tension that's caused by that external load. Even though we've got 25,000 pounds spread over 16 bolts, which would mean an average of 1,590 pounds per bolt, the total additional tension in each bolt due to that load is only 301.7 pounds. So not very much. Now, what's the preload? Let's see if, in order to find out whether we're going to be the total tension is less than the proof load, we need to find out what the preload is. So 0.75 times the proof load. Well, what's the proof load? All right, let's look these things up. For our bolt AT, our tensile stress area, we already calculated that, actually. We already have that. We found that from the table, 0.334 inches squared. And the proof strength of our material, let's say we're using grade 5 bolts. All right, grade 5, the material for bolts between 1/4 and 1 inch in diameter, our proof strength is 85 KSI. Okay, so our proof load is 28.39 kips. So our preload for a non-permanent connection is just 75% of that. So this here is going to be 21.29 kips. All right, then the total tension in the bolt is the sum of these two things. We've got FB is equal to 21,293 actually pounds plus just a measly 301.7 pounds that's due to the externally applied load. So almost all of it is preload. And we get a grand total of 21.59 kips. All right, so is 21.59 kips less than or equal to 28.39 kips? Yes, it is. So our bolts are fine. We've only got an additional tension of 301.7 pounds for each of these bolts compared to the 21,000 pounds that we preloaded it to. So it's almost inconsequential what the applied load is. We could increase the applied load greatly and we still would not exceed the proof load of those bolts.